beaker of carbonic acid. All right, we talked about both of those, although we'll look at the hydrochloric acid when we get back to the break with the digestive system and the stomach production. All right? So as I mentioned earlier, when we were doing the respiratory system, hydrochloric acid dissociates to form a hydrogen ion and a chloride ion. Carbonic acid dissociates the double-headed arrow means it can go either direction to form a single hydrogen ion and a bicarbonate ion. All right, so we have hydrogen ions formed by both of these. However, hydrochloric acid is considered to be a stronger acid than is carbonic acid. And which of these statements, A or B, provides the correct reason why hydrochloric acid is considered to be the strong acid? Carbonic acid is considered to be the weak. And we went over this about 2 weeks ago. So let's see if you could. All right, let's go back to the previous image. That will give you a clue.
I'm so good at chemistry, so I don't know what answer this is. I think this is B.
The answer's up on the board too, as far as a clue towards the answer. Okay. So how many hydrogen ions does hydrochloric acid release? One. How many hydrogen ions does carbonic acid release? One. Even though it has two, it only releases one. All right, the hydrochloric acid has only one to release, so it can't be A. It can only release one hydrogen ion, right? And carbonic acid only releases one. So when we look at the image, all of the hydrogen chloride are completely dissociated. Hydrogen chloride is in a solution, 100% of it dissociates to form a hydrogen ion. A weak acid like carbonic acid, about 10%. Okay? About 10% of the carbonic acid molecules will release. If we have 100 hydrochloric acid molecules, we'll have 100 hydrogen ions. If we have 100 carbonic acid molecules, we'll have about 10 hydrogen ions. Okay? I was trying to find a more specific number than that. 2% was about the closest I could get to for a weak acid. But to show you how weak carbonic acid is, it is weaker than acetic acid, which is vinegar. Okay? So, however, this is what allows it to work as a buffer. When we look at our acid-base system, we need to have buffers to buffer the range of pH that is appropriate for the body. So why is pH so important? Anybody know what the range of pH is in the human body? So pH in the human is 7.4. Put it in parentheses, 7.45. Okay? And then it ranges up or down by about 0.5. But 7.4 is given as the basic range. All right, so 7.35 to 7.45, you'll see a little bit of variation in there. Why is pH so important? What happens when we have extra hydrogen ions or we have fewer hydrogen ions? What's the molecule that's most affected by pH? What type of molecule? Not looking more for lipids, carbohydrates, or proteins. Protein. It affects the shape of proteins. So if the pH is too high or too low, the protein, if it's an enzyme, won't be able to work very efficiently. If it's a receptor, it won't be recognizing its component that it's going to bind with. All right. If it's binding oxygen, if it's shape changes depending on the pH. And so that's why it's very important for the body, not so much for carbs and fats as it is for the proteins that are functioning. And that's why the body is so careful to maintain homeostasis and maintain the pH within that narrow range. So when we talk about pH regulation, we're going to look at hydrogen ions, and we're going to look at, which in relationship comes from our CO2 values, all right? And we're going to look at bicarbonate ions. And you would think that comes from CO2 as well, but this is considered to have a much more of a relationship to metabolism, to other body processes, when we look at the balance between these two. Okay, that will make more sense as we move farther on. So we've talked about pH as a respiratory system, as it affected our respiratory system because of the hydrogen ions formed by carbonic acid in CSF. And it is hydrogen ions that affect the chemoreceptors in the aortic sinus and the carotid bodies of the carotid arteries. Even though we talked about oxygen, the oxygen, remember, has to drop below 60, a PO2 of 60 before that, and it's not very often the PO2 of your arterial blood is below 60, all right? So it's the hydrogen ions in the arterial blood that are more commonly going to change your respiratory rate, and then the CO2 converted to hydrogen ions in your CSF. So we need to talk about a buffering system, all right? So which of these may function as a physiological buffer? Two answers. So while you're thinking about that, what does a buffer do? Well, we're talking about a chemical buffer. A buffer on a boat is going to keep it from banging into the dock, okay, or against another boat. When we talk about chemically, I need to make some buffers. What does a buffer do? It has to be able to do two things. It has to buffer an acidic pH, and it has to buffer a basic or an alkaline pH, all right? So a buffer is able to do one of them, either of the following. Accept the hydrogen ion. Would hydrochloric acid be able to accept the hydrogen ion and we have just chloride? Is it going to bind to hydrogen and come back together and form HCl? No, because it just dissociates. It's never going to. If we have a lot of hydrogen ions in solution, you're still not going to see hydrogen and chloride come back together and take the hydrogen ion out of solution. It's too strong an acid. There's too much dissociation to occur there. So either accepts a hydrogen ion or it donates, gives up. And again, this is not driven by enzymes, this is not driven by hormones, this is driven by a concentration gradient. All right, so it would accept a hydrogen ion under what conditions? Acidic or alkaline? Acidic or basic? Acidic. Because if we have too many hydrogen ions, is our pH low or high? Low. So, under acidic conditions, there are too many hydrogen ions. All right, so they're going to be driven by concentration levels to bind to a weak or acid. So if we have our carbonic acid, all right, is this going to exist in an acidic condition? Or is it going to be in this form? Which of these will we most likely to see in an acidic condition? Because it has accepted a hydrogen ion. Therefore, it's buffered. It's removed one of those hydrogen ions that we have too many of, all right? So if we have lots and lots of hydrogen ions, one of them is going to bind to a bicarbonate ion and convert it to carbonic acid and take one free hydrogen ion out of solution, okay? Now, if we take that same molecule and we put it in a condition where there are not enough hydrogen ions and our pH is too high, then this is going to release a hydrogen ion to lower the pH and make the environment more acidic. And it would exist in this condition. So in this case, it has donated a hydrogen ion when conditions are basic or alkyl.
That would require a weak acid?
Pardon?
Would that require a weak acid?
Yes.
Okay.
Carbonic acid is a weak acid. Okay? So this would occur when there are alkaline or basic conditions, all right? Not enough hydrogen ions. Okay? So if I ask you a question on an electric exam or on a quiz, and I say, so this can exist in this form or this form, and I show you this form, and I say, so is the environment, is the solution that we find this in acidic or basic?
Then that's basic. because-
Basic, because it has released a hydrogen ion trying to lower the pH. So this will be the condition when the pH is too high, and it's trying to lower the pH by adding hydrogen ions to solution. All right? Whereas if it's in this condition, there were too many hydrogen ions, and this has accepted that hydrogen ion, trying to remove 3 hydrogen ions and raise the pH. Okay? So, in case you've forgotten, a high concentration of hydrogen ions equals a low pH. Sometimes it seems backwards, okay? A low concentration of hydrogen ions equals a high pH. So if we have a low pH, we have too many hydrogen ions, and the bicarbonate ion, if it's available, will bind some of those free hydrogen to try to take them, because it doesn't act as a hydrogen ion, and it doesn't affect the pH when we see it as the carbonic acid form, okay? So this is not, this hydrogen here would affect the pH. This one does not, except by raising it, because it takes that hydrogen ion out of solution. Okay, so that's what we look for in a buffer. A weak acid or a weak base, either one can release a hydrogen or accept a hydrogen, okay? Strong acids are strong. Sodium hydroxide is a strong base. In solution, it would be sodium and a hydroxyl group, OH, okay? So that doesn't work as a buffer. So these are the major buffer systems that we see in the body to help the body maintain that narrow range. So typically inside the cell, we have phosphate buffers, and we have proteins, can be either inside the cell or in extracellular fluid. Carbonic acid is our major extracellular fluid, okay? So proteins can be in either system. Interestingly, the only place we're going to talk about phosphate is as an extracellular buffer. It's very important in urine as an extracellular fluid, okay? But other than that, it's important in cells, and proteins are important in cells. Proteins are important outside the cells, and carbonic acid is important outside the cell, okay? So we'll look at examples of these, and then we're going to focus on the urinary system for the last little bit. So, I'm going to leave that up on the board while we talk about protein buffers, okay? May I erase the board? Just have that down? Okay. So what we're looking at is the structure of an amino acid. The R means that there are additional amino acids. You can think of the R as a rest, all right? So a protein is just a long string of amino acids that can be folded into shapes. So it has a nitrogenous end and an acid or hydroxyl end, all right? So here's the nitrogen, it and here's the hydroxyl group. Notice the two hydrogens, one is in red and one is in blue, okay? So this is how our protein buffer works. So essentially, we have our nitrogen and our carbons. This is going to mean the rest of the amino acids are attached here. And we have a hydrogen. Nitrogen can attach three components. It can either have another hydrogen if it's just nitrogen all by itself. When we add a fourth nitrogen, so we have nitrogen on a fourth hydrogen. If you have nitrogen all by itself, it's written like this, it's an ammonia group, all right? If we add a fourth hydrogen, this becomes an ammonium ion. All right, so this is ammonia. And this is an ammonium ion, okay? So that adds an extra charge, okay? So, a buffer has to be able to accept a hydrogen or to release a hydrogen, all right? So if we are accepting a hydrogen, this oxygen is already going to have its hydrogen attached to it as an hydroxyl group. And we add this extra hydrogen, okay? If this buffer is donating a hydrogen, we certainly don't add the extra one, and we get rid of this one, and this becomes a negative charge, okay? So those are the two forms at which this goes back and forth. So if we're accepting a hydrogen, we have this hydrogen attached, and we have that hydrogen attached. Okay, so that's the view that you see in the question. So is this buffering an acid, or is this buffering a basic or alkaline solution? An acid, because it's accepted the hydrogens, all right? So a buffer will accept hydrogens when it's in an acidic condition, trying to reduce the number of free hydrogens, and it will release hydrogens as ions when it's in a basic condition and it's trying to add hydrogens and lower the pH. So this would be in an acidic condition when there's lots of hydrogen ions in solution around it. And again, it's driven by the number of free hydrogen ions, right? So if there's lots of free hydrogen ions, our pH is going to be acidic, and our amino acid, our protein, will accept hydrogens. Then if there are not enough hydrogens, our pH would be basic or alkaline. And we're going to remove these extra hydrogens and release these. And that would be under basic conditions. Trying to add free hydrogens to the solution to lower the pH. Okay? So that's how protein works as a buffer. This is how hemoglobin works as a buffer inside the red blood cell. And there's CO2 being picked up from the tissues. It's how proteins work that are just regular proteins in the blood or extracellular fluid. Okay? So here's a diagram illustrating what we just went over on the board if you want to go back and look at it on the PowerPoint. So notice there's no hydrogen here and there's no hydrogen here. Or there is a hydrogen in both places. Okay? All right, so which of the following is a carbonic acid buffering molecule which is seen in the basic? So this would be what we just went over prior to the protein. So we're in a basic solution. So is it going to be the accepted hydrogen one, or is it going to be the one that has lost hydrogen? So, we really have already talked about the carbonic acid solution, and we're gonna talk about it again with the kidneys. So I'm gonna essentially just skip over that side. Alright, so here we have the urinary system. Now, before I move into this, because this has several different buffer systems associated with it. So we're working with carbonic acid. We have the ammonia group. Remember we talked about the secreting that. So NH3 plus a hydrogen becomes our ammonium ion, so that's a buffer. And here's the phosphate buffer system. In case it's too small for you to see in the back. Okay, H2PO4 goes back and forth between just HPO4 and 2 negatives. So the other one is like that, okay? So which one of these would we find in an acidic condition? Top one, because it has the extra hydrogen. And this would be in a basic solution because it has given up one of the hydrogens, okay? When you make this, if you work in a lab and you're making a phosphate buffer for growing cells, it usually uses a sodium biphosphate, all right? So if you're working a sodium biphosphate, sodium bisphosphate is more commonly done. All right, so before we look at this, let's make sure I'm headed in the right, yeah. So we've talked about chemicals being buffers, all right? But we have the respiratory system that works as a buffer. So what are the respiratory changes that we talked about? How would the respiratory change, the respiratory rate or system change if your pH, you had too many hydrogen ions in your arterial blood? What would happen to your respiratory rate and or depth?
Would it slow?
So would it go up or would it go down? Would you be breathing off more CO2 or retaining CO2? What would the body try to do? Breathing it off. So if your pH is too low, you have too many hydrogen ions, because your protein buffer and your other buffers aren't working, your respiratory system is going to change to increase your respiratory rate, to get rid of CO2 at a faster component. So you're going to breathe more fast, rapidly, and you're going to breathe deeper. Okay, you're going to blow off CO2. Now, let's say you are in ketoacidosis. Okay, you're diabetic and you don't have enough of the simple sugars, and you start breaking down your fat for energy, and you release fatty acids. So you're in ketoacidosis because of the fatty acids being released from the fat breakdown. Your pH starts to drop. You're going to be doing the extra breathing. Now let's say that you are in metabolic alkalosis. Maybe you've overdosed on a bottle of Tums. All right, what's going to happen to your respiratory rate? It's going to decrease. Now, can you ever balance it with your respiratory rate change? You got to take a breath. You can't just stop breathing in an attempt to compensate for that. But your breathing would slow down, become more shallow, so that you're retaining CO2, which makes more carbonic acid, which dissociates to release more hydrogen ions. Okay? Now, so that's how the body system would work. But if you have a respiratory disease, if you have COPD, you have asthma, you have too much CO2 in your body, changing your respiratory rate is not going to help. That's the reason you have a problem, okay? So if the problem is respiratory compensation isn't going to work. We need to do some other type of compensation, and that's typically in the urinary system, okay? So I'm going to focus primarily on the proximal convoluted tubule, and then I'm just going to tell you that the collecting duct, or the distal convoluted tubule, but primarily the collecting ducts can also do the reverse. So let me tell you what the proximal can do. So let's draw that same relationship of the cell we showed for secondary active transport. So we are in the proximal convoluted tubule, all right. Filtrate just got through saying that we are in acidosis. And hydrogen ions tend to fuse out of the blood. All right? But they cannot pass through the basal membrane of our cell. Remember how they couldn't get through the membrane of lining the CSF? They couldn't get through the ependymal cells? So how did we bypass that problem? We couldn't get the hydrogen ions in our blood to get into the CSF where the receptors were, so what did we do instead? What could go across into the CSF? Carbon dioxide as a gas. So, in the blood, we take the hydrogen ions and we add it to bicarbonate, and that makes carbonic acid. Told you you're going to see a lot of this. And then that dissociates to form water and carbon dioxide. Okay? Remember, we're trying to secrete hydrogen ions. We're trying to buffer. We can't breathe off enough hydrogen ions. It's not working. Our pH is still acidic. So we're going to move hydrogen ions in this direction. All right? But they won't cross that membrane, so we have to get around that by converting them back to carbonic acid, to water, and to CO2. That doesn't give us any hydrogen ions, does it? There's no hydrogen ions in that CO2. But there are some hydrogen and there's water in the cell. So now we do this in reverse. Carbon dioxide moves into the cell. And remember this molecule? We've talked about it being in two places already. It's inside the red blood cell, and it's inside the cerebrospinal fluid. Do you remember what CA stands for? Pardon? Carbonic, not quite, and hydrate. So that enzyme increases the rate of the reaction. We don't have it in the plasma, okay? We have it in red blood cells, but not in the fluid of the plasma itself. So we have it in three places. We have it inside the red blood cell, we have it in the CSF, and now we have it in the proximal convoluted tubules and their simple cuboidal cells. All right, so that makes this occur a little bit faster. And now that makes carbonic acid, which dissociates to form hydrogen ions, and bicarbonate. And the bicarbonate ions go back into the blood. And that's how our CO2 gets back to the blood. Okay? And now the hydrogen is pumped. It goes as an antiport with sodium. And now hydrogen is in our filtrate. What's it going to do to the pH of filtrate? It's going to lower it. Remember when we talked about urine characteristics on Thursday? We said the pH of urine is normally around 5 to 6. It could go a little over 7, but not usually. It would be down around 2 or 3 with all the hydrogen ions we secrete if we did not use this buffer system, okay? Especially the phosphate buffer system. So here's where we find phosphate as a buffer outside of the cell, because this is in the filtrate. Okay? So the buffer, these three buffer systems in the filtrate fluid allow additional hydrogen that would be comfortable. Talk about burning urine. All right. The pH of 1 or 2 in our urine would not be very comfortable. And so this creates a sink that allows additional hydrogen to move into the system. Now, in addition to that, we can add bicarbonate back to the blood. So here we've secreted, we're secreting hydrogen ions, right? If we move bicarbonate from here back to the blood, what do we call that process? Filtrate to blood is what called what? Reabsorption, all right? So we're gonna go reabsorb bicarbonate ions. Again, I don't know why. Bicarbonate ions will not cross the membrane of the microvilli. So guess what we have to do? We have to flip this around, take bicarbonate ions, hydrogen, or carbonic acid without the carbonic anhydrase, disassociate that into water and CO2. And then inside the simple cuboidal cell, we go through the same reaction with the carbonic anhydrase. And the bicarbonate ion now is reabsorbed back to the blood. So we're doing a double whammy for controlling the pH. We're secreting hydrogen ions, so we're getting rid of the hydrogen ions, and then we're reabsorbing bicarb that was filtered and adding that, so we have additional bicarbonate ions to buffer the hydrogen ions that did get filtered, that did get secreted. Let me say that again, okay? So this is going to be under acidic conditions. So the pH is too low. So we want to get rid of hydrogen ions. Hydrogen ions are lowering our pH. And we can't get them to cross the bottom membrane of the simple cuboidal cells. So we convert it to carbon dioxide. We convert that back into hydrogen ions. And the hydrogen ions are pumped into the filtrate, okay? Now, we can buffer even more by hydrogen ions if we had more bicarbonate. So we take bicarbonate that's in the filtrate, that was filtered, and we reabsorb it back into the blood. And now we have even more bicarbs than we had before, that we can buffer any remaining hydrogen ions, okay? So that's what happens when the pH is too low. What happens when the pH is too high? Do we want to get rid of hydrogen ions? No. Do we want to add any more bicarb to the body? No. So this system stops. We don't reverse it in the proximal convoluted tubule. It can only go in this direction. Okay? But it can be reversed in a collecting ducts. So the alpha cells are going to be, this is in the collecting duct, the alpha cells are going to be just like our proximal convoluted tubule, okay? They can only secrete hydrogen ions and reabsorb bicarbonate ions. Our beta cells do the flip. So these will be active. These will stop, the proximal convoluted tubule stops functioning for secretion and reabsorption of hydrogen and bicarb when the conditions are alkaline. The alpha cells stop functioning and the beta cells become active under alkaline. So think of beta and basic. Okay? So acid and alpha, acidic conditions, the alpha cells work, and the proximal convoluted tubules work. And basic conditions, those two stop, and the beta cells will become active. And they will secrete bicarb, getting rid of bicarb, and reabsorb hydrogen to lower the pH of the body. Okay? We have the respiratory system to change respirations up or down. And we have the urinary system to secrete hydrogen ions or not, and to secrete bicarbonate. So let's compare if your respiratory system changes so that you have decreased your respirations. Your respirations have slowed down and they are shallow, what is your urinary system gonna be doing? Is it gonna be secreting hydrogen ions, or is it gonna be secreting bicarb? Your respiratory system is slowed. Are you trying to get more hydrogen ions with a lower respiration, or are you trying to get rid of hydrogen ions? You're trying to get more CO2, right? If your respiration is slow and shallow, you're trying to keep CO2. CO2 is going to be converted to carbonic acid, which is some of it's going to release hydrogen ions. 10% of it's going to release hydrogen ions. So we're trying to get more hydrogen ions. So our pH is too high. We're decreasing our respiratory rate in order to add hydrogen ions. So we're not going to be getting rid of hydrogen ions, right? So the proximal convoluted tubule is not going to be working if your respiratory rate has slowed down. Your alpha cells are not going to be working if your respiratory rate has slowed down. But your beta cells will be, because this is another way of adding the hydrogen ions by reabsorbing. We're adding hydrogen, we're reabsorbing hydrogen via the beta cells.
We're reabsorbing them into the collecting bag.
Well, we're reabsorbing them, no, we're reabsorbing them into the blood. Okay? May I erase the board and I'll just kind of write that as a chart for you? Did I have what's on the board, the diagram on the board? Okay. All right, so if the body is in a basic pH, too many tongues, throwing up, losing your hydrochloric acid from too much vomiting. We don't have enough hydrogen ions, okay? Under this condition, respiratory rate and depth is going to decrease, because that allows us to increase arterial CO2, which results in an increase in carbonic acid, which results in an increase of hydrogen ions. Does that make sense? We've added more hydrogen ions to our body because we didn't have enough. Okay? That's what the respiratory system's going to do. All right? Our protein buffer. So if we have a protein buffer, is this going to have hydrogens on it, or is it not? Not. Okay? Because it's released the hydrogen ions to the fluid. All right? Does that make sense? All right, urinary system, then, proximal convoluted tubule has stopped secreting hydrogen ions, and it has stopped reabsorbing bicarbonate. And again, we're trying to keep those hydrogens and not get rid of them, all right? Same thing. The alpha cells and the collecting duct have stopped. Because they do the same thing as the proximal convoluted tubule. However, our beta cells and the collecting duct now secretes bicarb and reabsorbs hydrogen ions. Okay? All of that is going to increase the amount of free hydrogen ions in the body and lower the pH and make it more acidic. Okay? So if the body's pH is basic, to make it more acidic, it will do those things. Okay? too many hydrogen ions, right? This would occur with diarrhea, okay? Losing the bicarbonate ions that the pancreas produces, and now we're reabsorbing the hydrogen ions from the stomach, and we don't have the bicarb from the pancreas to reabsorb it. Ketoacidosis, okay? Pneumonia or COPD, where we're keeping too much carbon dioxide in the blood, it's going to be converted to carbonic acid. If it's a respiratory problem, this isn't going to work very well, okay? But if it's not a respiratory problem, we'll see the respiratory change. So if it's ketoacidosis, we'll see this. So instead, the respiratory rate and depth will increase, okay? With the loss of CO2, meaning less bicarb, carbonic acid, meaning less hydrogen ions. That will be the change if it's an acidic pH, unless it's a respiratory problem and then this doesn't work. Okay? Our protein buffers will show extra ions on them. Okay? And our beta cells will stop. Okay. So that's the urinary system effect and the other buffer components of acid pH. Now we're going to look at the lab, okay, the extra credit part of the lab, which is figuring out, using Hasselbalch's equation, figuring out, it's okay, it's okay.
She said no.
Okay, I just heard a no and a. So, how do we get the number 7.4 for a pH? Anybody know? It's an Hasselbalch equation, which has logarithms and anti-logarithms and all of that.
So does that mean it's not gonna be on the test?
It means you don't have to figure it out on the test. The
Okay.
questions about it will be on the test. But I'm gonna show you a computer site if you don't have a calculator or calculator. Mechanisms are weird. I'm gonna show you a computer site. So when let me pull those slides up. And if you have your lab packet, the extra credit part are a couple of pages of tables of patients.